Hey guys, how are you doing? This is the first video on the chemistry part of the IMAT, on the section 3 IMAT Chemistry. This section has 12 questions and in my opinion I believe one can easily answer 10 correctly out of them. Biology, I believe it is more difficult, and logic is way more difficult. But chemistry, I believe, is one of the easy parts. So just stay focused and I believe we can ace this together. Let's get going right away. In this video, I'm going to cover the composition of matter, the first topic. Let's get going. First of all, the states of matter. We've got 3 states of matter: solid, liquid, and gas. Let's see one per one. First of all, solid. What is solid? Your book, my computer, my cell phone, a piece of paper. These are solid. These have definite shape and definite volume. What happens now in a molecular level? The particles are close together and many times are locked into a very regular framework. This is how the particles are together. And we've got positive, negative, positive, negative, positive, negative. They are interchanging between them. I'm not sure if that is a correct word. There is a slight molecular motion and mostly in the types of vibration. So this molecule here is vibrating. Of course, these lines, they do not exist in reality. It's just attractions between atoms. Okay, and if we want to say that a substance is in the solid level, we put into parentheses the sign S. So if I give you H2O, which is water, and the S sign into parentheses, that means I'm talking about solid water, which is ice. Okay. Then we've got the liquid. Liquids have a definite volume. That means what? That if I come here with a big device as the water and I push, it won't be able to be pushed because it has a definite volume, but they do not have a definite shape and they conform to the container in which it is placed. We are all familiar with liquids and how they conform to the shape of the container. What we have here, we have clumps of particles moving relatively free among other particles, and it is indicated by the sign L into parentheses. And last, we've got gas, which has not definite shape and not definite volume. You can see that here. It expands to fill the container which is placed. It can be pushed until a certain point, of course. And the particles move rapidly with respect to each other and act basically independent. They act independently of each other. Okay. It is indicated by the sign G. We're going to talk about more gas a bit later, but first of all, let's see how we can change between the different states of matter. First of all, let's say I want to change something from solid to become liquid. This is called melting, and we're all familiar with it. Why melting takes place? Because the energy transferred to the solid when we heat a solid, it makes the particles vibrate more vigorously. Since they vibrate more vigorously, they may break off from the crystal lattice, and therefore they will start to move more freely than before. Also, since we are providing energy to the solid, we are giving energy to break the bonds. So the forces of attraction between the particles will weaken. And last, the solid changes to liquid when its temperature is sufficiently high. Alright, and this is the state of melting. Now, let's say we've got a liquid. If we heat it, if we have a solid and we heat it, it will become liquid. If we've got a liquid and we cool it, it will become solid. So what happens? First of all, when we cool it, it loses kinetic energy. The particles lose kinetic energy. And they are starting to take more specific positions, and they're not moving freely. Since we're cooling it, we're taking energy away from the system, and therefore we are making them create bonds. Therefore, the force of attraction starts to increasing, and now we have molecules staying in specific positions, more steady, and now it started to become solid. Okay, and this is the process of freezing. Now, if I heat a liquid, we will have vapor, gas. It will go to the gas state, and this is the process of vaporization. What happens? The energy transfer to the liquid makes the particles move faster. And what is a characteristic of the gas? The particles move rapidly with respect to each other and independently. So we've got very few, almost none bonds. Okay, so we start to break all bonds, and therefore we've got free movement, and they can go wherever they are, they lose their specific volume, and they become gas. Now we heat, therefore the forces weaken. The particles with most energy are the first to escape from the forces holding them together. The liquid starts to evaporate, and the forces weaken enough for all the particles to become completely free from each other. And now we've got boiling, which is it's becoming gas at a maximum rate. This is the process of vaporization, and it's the process of changing the state of a liquid to the gas state. Now, the energy required to change 1 mole of liquid to 1 mole of gas is called the enthalpy change of vaporization. And I want to ask you something. Are you familiar with this word? Mole. What is it? You see, I have decided to present my videos in chemistry according to the order that it is on the IMAT specification. But we are asked to talk about moles later on chemical reactions and stoichiometry. So I'm not going to talk about moles here. I just want you, in order to understand what a mole is a way to measure how much substance we have. Okay, it's more complex than that, but the general idea is that it's a unit of measurement of how much substance we've got. So when I change 1 mole of liquid, that means a specific amount of substance. Okay, to 1 mole of gas. Again, a specific amount of substance is presented by the word mole. All right. Now, when we cool a vapor, what will it become? A liquid. This is the process of condensation. It loses kinetic energy, so the molecules move around less quickly. They experience increasing force of attractions, and they start to move more slowly and become closer together when the pressure temperature is sufficiently low, and the gas liquefies. Now, the solid state. I want to talk about the crystal lattice a little bit more right now. What is the crystal lattice? You see, many ionic, metallic, and covalent compounds are crystalline. The regular structure of crystals is due to the regular packing of the particles within the crystal. We call this regular repeating arrangement of ions, atoms, or molecules a crystal lattice. And we've got ionic lattices and metallic lattices. Ionic lattices have a three-dimensional arrangement of alternating positive and negative ions. The compounds with ionic lattices are sometimes called giant ionic structures. Alright, they're usually cubic. Now, metallic lattices are ions surrounded by a sea of electrons, and let me get a little bit more details about metallic lattices. A metallic lattice consists of ions surrounded by a sea of electrons. The ions are often packed in hexagonal layers or in a cubic arrangement. When a force is applied, the layers can slide over each other. But in a metallic bond, the attractive forces between the metal ions and the delocalized electrons act in all directions. So when the layers slide, new metallic bonds are easily reformed between ions in new lattice position and the delocalized electrons. The delocalized electrons continue to hold the ions in the lattice together. The metal now has a different shape. This explains why metals are malleable, that means they can be hammered into different shapes, and ductile, they can be drawn into wires. The high tensile strength and hardness of most metals is also due to the strong attractive forces between the metal ions and the delocalized electrons. And now we're going to talk about gases, because it asks us to talk about ideal gas laws. And let's get right into it. First of all, I told you ideal gas, it says here. What on earth is that? An ideal gas is a gas that obeys the kinetic molecular theory, that obeys these 5 postulates, 1, 2, 3, 4, 5. It's called an ideal gas. And what does the kinetic molecular theory tells us? First of all, the kinetic molecular theory, or KMT, as I will be referring from now on to it, attempts to represent the properties of gases by modeling the gas particles themselves at the microscopic level. There are 5 main postulates of the kinetic molecular theory. First of all, gases are composed of very small particles, either molecules or atoms. Okay, that's understandable. The gas particles are tiny in comparison to the distance between them, so we assume that the volume of the gas particles themselves is negligible. And this is why the gas overall does not have a specific volume, because the molecules don't have a minimum volume they can exist, because we consider them negligible. Okay. Now, these gas particles are in constant motion, moving in straight lines in a random fashion and colliding with each other and the inside walls of the container. Now, because they are colliding, let me draw something for you. Let me get here to draw it here because I have more space. This is a container. And let's say this is a particle. It will collide with the wall. That means it acts a force in the wall. Where there is force, there is pressure. Right? So, when there is pressure, there is force. And this is the pressure of all. If we add all these pressures due to all these forces, we see that this is constant. It remains constant. And it is the pressure of the gas. Alright, let's go to postulate 4. The gas particles are assumed to neither attract nor repel each other. They may collide with each other, but if they do, the collisions are assumed to be elastic. As you will see when you review your physics knowledge, you will see that elastic is a collision where the kinetic energy remains constant. That means they do not lose their kinetic energy. We don't have any type of loss, like heat loss, due to these collisions. Okay. Now, the average kinetic energy of the gas is proportional to the Kelvin temperature. And we will see that now. Now, a gas that obeys these 5 postulates is called an ideal gas. However, just as there are no ideal students, there are no ideal gases, only gases that approach ideal behavior. We know that real gas particles do occupy a certain finite volume, and we know that there are interactions between real gas particles. These factors causes real gases to deviate a little from the ideal behavior of the kinetic molecular theory. But a nonpolar gas at low temperature and high temperature would come pretty close to ideal behavior. I could show you what happens in the non-ideal behavior, and there are some parts in our textbooks, but I've looked at the specification and it does not say anything about non-ideal gases. And in the composition mine says ideal gas laws, and there are non-ideal gas behavior that we could look into it, but I don't believe we should, because the specification does not mention anything, so I'm not. Now, before we leave the kinetic molecular theory and start examining the gas law relationship, let's quantify a couple of the postulates of the KMT. we saw postulate 3, and it describes the motion of the gas particles. It says, the postulate 3, that the gas particles are in straight motion, moving in straight lines, in random fashion, colliding with each other and the inside walls of the container. Alright, at what speed are they moving? The average velocity of the gas particles is called the root mean square speed, and it is given by the symbol URMS, root mean square, root of the mean square. I don't know. This is a special type of average speed. It is a speed of a gas particle having the average kinetic energy of the gas particles. So it can be represented like that. Alright. R is the molar gas constant, and we'll talk more about it later. T is the temperature in Kelvin degrees, and if I give you the temperature in degrees Celsius, do you know how to convert it into degrees Kelvin? It's really easy. You just add 273. Here is the T in Kelvin is if you add in the temperature in Celsius 273. Really easy. Alright, and M stands for the molar mass of the gas. Now these root mean square speeds are very, very high. Hydrogen gas, for instance, at 20 degrees Celsius has a value of approximately 2000 meters per second. That's a very, very high speed. Now postulate 5, you remember what it says? That the average kinetic energy of the gas is proportional to the Kelvin temperature. Why? Now, let's see mathematically how we can represent the average kinetic energy per molecule. Average kinetic energy per molecule. It's this one, you all know it. But the average kinetic energy per mole of gas is represented by 3/2 RT. And you see that the average kinetic energy is proportional to the temperature in Kelvin degrees. Amazing? I know. And now we're going to get into gas law relationships. The gas laws relate the physical properties of volume, pressure, temperature, and moles. Moles, I said, it's another word for amount, to each other. First, we will examine the individual gas law relationships. Alright, then we will combine the relationship into a single equation. But before we do that, let's describe a few things concerning pressure. When we use the word pressure, we may be referring to the pressure of a gas inside a container or the atmospheric pressure. It's the pressure the pressure that is being applied to us by the atmosphere above us. Now, these two different types of pressure are measured in slightly different ways. Atmospheric pressure is measured using a barometer, and I want to explain you, this is a barometer, and how it is measured in order to understand how much one type of specific unit measurement of pressure, milligrams mm of mercury, mm of mercury. So in order to understand that, we need to explain the barometer, the mercury barometer. So, an evacuated hollow tube sealed at one end, you see, sealed end, is filled with mercury, and then the open end is immersed in a pool of mercury. So we've got mercury and mercury. Now, you will believe that gravity will tend to pull the liquid level inside the tube down, while the weight of the atmospheric gases on the surface of the mercury pool, here the air pressure, will tend to force the liquid up into the tube. These two opposing forces will quickly balance each other, and the column of mercury inside the tube will stabilize. The height of the column of mercury above the surface of the mercury pool is called the atmospheric pressure. At sea level, the column averages at 760 millimeters high. The pressure is also called 1 atmosphere, atm. Commonly, the unit torr is used for pressure, where 1 torr, 1 millimeters of mercury, so that atmospheric pressure at sea levels equals 760 torr. Alright. Now, to measure the gas inside a container, here, we use a manometer. As in the barometer, the pressure of the gas is balanced against a column of mercury. Nothing different. Okay. And now let's get into the gas law relationships. First of all, the volume pressure relationship, Boyle's law. Boyle's law describes the relationship between the volume and the pressure of a gas, the volume and the pressure of the gas, V for volume and P for pressure, when the temperature and the moles, the amount, is constant. If we have a container and we decrease the volume of the container, the pressure of the gas increases because the number of collisions of gas particles with the containers inside walls increases. Mathematically, this is an inverse relationship, so the product of pressure with volume is a constant. Okay. If we take an initial volume 1 and pressure 1 with amount and temperature constant and change the volume, and the pressure will change as well, we can relate the two sets of conditions to its equations. There are exercises here, and I will talk in the end of the video about these exercises. In this mathematical statement of Boyle's law, if we know any of these three quantities, we can calculate the fourth. Then we've got the Charles law, which associates volume with temperature when the pressure and the amount are constant. If a sample of gas is heated, the volume must increase for the pressure to remain constant. So there is a direct relationship between the Kelvin temperature and the volume. As one increases, the other also increases. This is represented mathematically like this. V over T is constant. Okay. Again, if there is a change from one set volume temperature conditions to another, Charles Jones can be present V1 over T1 equals V2 over T2. And we get moving. Then we've got Gay-Lussac's law, which they associate pressure and temperature while keeping the volume and the amount of gas constant. As the gas is heated, the particles move with greater kinetic energy, striking the inside walls of the container more often and with greater force. This causes the pressure of the gas to increase. So P over T is constant, and it can be expressed as well as P1 over T1 equals P2 over T2. And the combined gas law, the only thing that we're keeping constant is the moles. That means the amount of substance. And what it says, PV over T equals P over V over T. Now, I have nothing to say now. This is the combined gas law. You can look at it. All right. P times V over T will remain constant. That is what you should know. And according to that, you can find all other laws. For instance, if we got V constant, V equals V accent. Therefore, this will leave, and we've got Pt over P1 Pt, P2 T2. If we got temperature constant, T will leave from both sides. Then we got PV equals P accent V accent. If I keep the pressure constant, I will have P with P will leave, and I will have V over T, V accent over T, and we've got all these three laws into one combined. Okay. According to what you have constant, it's time. And last, we've got the Avogadro's law. In all the gas law problems so far, the amount of gas has been constant. But what if the amount changes? That is where Avogadro's law comes into play. If a container is kept at constant pressure and temperature, and we increase the number of gas particles in that container, the volume will have to increase in order to keep the pressure constant. That means that there is a direct relationship between the volume and the number of moles and of gas. This is Avogadro's law, and it looks like that. And last but not least, we've got the ideal gas equation. It has this mathematical form where P is the pressure of the gas in atmosphere, millimeter of mercury, anyway, all this. V is the volume in gas, the volume of the gas. N is the number of moles in the gas. T is the Kelvin temperature, and R is the ideal gas content. This is the value of R if the volume is expressed in liters, the pressure in atmospheres and the pressure in Kelvin, 0.0821. That one. Now, you can calculate the R for other units as well, but for these units, it's always that. And if you don't remember the units, you can find them out from that. We've got the ideal gas equation, and I isolate R. Therefore, R equals PV over NT. P is atmospheres, V is in liters, N mole, T, oh my god, I left it as T, it's Kelvin. Oh, I'm terrible. This is meant to be Kelvin. Okay, and then you've got the unit of R. Okay, so it's better to use the 0.0821 and convert the given volume to liters and the pressure to atmospheres. And always the temperature in Kelvin. Now Dalton's law of partial pressures. This is not an ideal gas law, but I thought I should include it. Anyway, Dalton's law says that in a mixture of gases, A, B, and C, the total pressure is simply the sum of the partial pressures. What are the partial pressures? Are the pressures associated with each individual gas. Therefore, we've got this equation: P total equals PA, the partial pressure of A, the partial plus the partial pressure of B, plus the partial pressure of C, etc. Now, commonly Dalton's law is used in calculations involving the collection of a gas over water. Anyway, if we know how many moles of each gas are in the mixture and the total pressure, we can calculate the partial pressure of each gas by multiplying the total pressure here, the total pressure, by the mole fraction of each gas. What is the mole fraction of each gas? It's that. The mole fraction of gas A would be equal to the moles of gas A divided by the total moles of gas in the mixture. And now let's talk about heterogeneous system. Is a system where the substances are not in the same state. For instance, a system where we've got liquids and gases and solids maybe, while in homogeneous system is a system to which all the substances are in the same state. So if I consider a system, my room, it is a heterogeneous system, because I got solid, my desk, I got liquid, I got a bottle of water here, and I got air, gas. So it is a heterogeneous system. If I consider a homogeneous system, it's if I take the glass outside, and if I take the bottle of water, if I take it outside of the room, and all the air is being subtracted from the room, therefore what will be in the room? Only solid stuff. Therefore the room will be a homogeneous system. That's all for today, guys. I wanted to say that in the gas laws there are many exercises where there are you have been given some values and you need to find the other values as well. So in this video, in the description below, today or tomorrow, I will upload a PDF file of solved exercises. I'm already working on it and I want to cover the most fundamental exercises. So this is why there are no exercises and how we solve them in this video, because in the description below, except the presentation links that I'm always so late in uploading, and I'm really sorry about that, but it is so boring uploading those presentation links. Anyway, except of the presentation link, there will be a file with exercises on how to solve solved exercises regarding the material covered in this video. So, oh yes, I haven't covered the part of compounds and elements. The part of elements will be covered in atomic structure and the periodic table, and the part of compounds will be covered on the chemical bonds topic. So I don't believe I should cover it yet. Be ready for in the next videos. Bye bye guys, and thank you for watching, and if you liked my video, please hit that thumbs up button. Bye bye.